Last time we introduced the idea of calculating electric forces, and we had the expression F was equal to KQQ over R squared, which was very similar to the gravity expression you guys had used. FG was equal to GMM over R squared. Very familiar in how it works and how the calculations work and stuff like that. So we're just going to do some practice with that and show you how this works. So let's just take something really simple. So here's a little positive charge. And let's say it is a 0.12 nanocoulomb charge, and let's say 7.2 micrometers away. Let's just put a proton there, and let's find the force on the proton. Okay, well that's a pretty straightforward calculation. It's just a straight application of the formula. So electrical force is KQQ over R squared. I've got the big Q, I've got the little q, I would call that my big Q. I've got the little q of the proton, I've got the radius, I've got everything needed to calculate that force. So if we punch all that stuff in, we should get around 3.33 times 10 to the negative 9 newtons. Okay, and that's basically it. It's just almost identical to calculating gravity. It's the same idea. Okay, now let's change this a little bit. What if I change that to an electron instead, the exact same place, the exact same anything, and I calculated with the electron? Well, the K is the same, big Q is the same, little q is the same, the radius is the same, everything would be the same. Except the only slight difference is if you did this for the electron, technically that little q is technically negative. So when you calculate the force, it is going to be negative 3.3 times 10 to negative 9 newtons. Now, I don't really like using the negatives. I talked about this before already. I don't really like doing that because all it tells me is that the two Q's are opposite and it's going to be attraction. So that right there, that just tells me that they are going to attract the same way the invisible positive over there tells me they're going to repel. And other than that, it doesn't really tell me which way it's going to go if I got a picture and stuff like that. I'd much rather look at the picture and finish the question off by going, hey, the force between the proton and the big Q is 3.3 to the negative 9, and the proton is going to want to go towards the right. And for the electron, it's negative 3. Well, I'd rather say, get rid of this, I'd rather say it's 3.3 to the negative 9 newtons, and the electron is going to want to go towards it or go to the left. So I'd much rather use arrows for this type of thing to sort of give an idea of what the charges are actually going to do. But that's the basic way to calculate the force. Okay, so let's take something similar and show you some other ways of how this works and connect it to the electric field stuff that you guys have taken as well. Okay, so let's take another question here. Let's go with, here's a positive charge, I'll call that Q1, and I'll say it's 0.82 nanocoulombs. And over here, I'm going to put another positive charge, and I'll call that Q2, and I'll say that is 0.60 nanocoulombs. And over here, I am going to put we're going to put an electron right there. Okay, and let's say these guys here are 1.4 millimeters apart, and let's say these guys are 0.9 millimeters apart, and let's find the force on the electron. Okay, now there's two forces acting on it. What's happening between Q1 and Q2, there's a force there, but that's absolutely irrelevant. That has nothing to do with anything we're doing right now. We're just going to find the two forces, and then we'll put them together sort of like we've done before. So I can find the force from number 1 is going to be KQ1Q, where the little q is my electron over here, divided by the radius 1 squared, and radius 1 would be the 1.4 millimeters. Make sure you make that to the negative 3, and we can calculate that force. And then over here, I would have force number 2 is going to be KQ2Q over radius 2 squared, and calculate that force as well. So punch out those values, and hopefully we'll get the same forces. Okay, so for force 1, I got 6.02 to the negative 13. Force number 2, I got 1.07 to the negative 12. And we can look at a couple other things. First of all, when I often do this, I like to have my powers of 10 to actually be the same. So I would prefer to rewrite either this one to the negative 13 or this one to the negative 12 to keep things nice. I just like having my powers of 10 the same, just so I can see the magnitude difference between my forces. Okay, so this one here, I can just change this one right here. And this would be 10.7 to the negative 13, or it can change this one as well. And I think I'm going to change this one to 0.602 times 10 to the negative 12 newtons. I just like having my powers 10 the same. All right, now in terms of forces, for my Q1 force between the electron and Q1, the electron would be attracted to it. It'd want to go towards it. So the force this one is applying is going towards the left. And for this one here, between these two, the electron obviously wants to go down. I'm going to erase this, get this out of the way here. That electron wants to go down towards it. So this force would be down. So we've got these two forces. One's going sideways, one's going down. It's a very similar type setup to when you guys did the electric fields. So I've got the two forces. I'm just going to put those two forces together as a triangle. So I've got one force going this way, and this is 0.602. And then I've got the other force going down, and this is 1.07. And this is one of the reasons I like to have my powers of 10 the same, so I can drop them when I make a triangle and just introduce them later. So then if I found the force would then be the hypotenuse of the triangle. So solve for the hypotenuse of the triangle, solve for our angle in there, and then we can keep on going from there. We'd have our final force. Okay, so I punched out the triangle, and I've got 1.23 as my hypotenuse, and the angle there is 61 degrees. So when I introduce, put it all together, the total force on the electron would be 1.23, bring the times negative 12 back well, this is 61 here. Remember, we want our angles from the positive x-axis, so we'd wrap it all around. So we'd add the 180 to it, so at around 241 degrees, and that would be the way the force of the electron would actually go, which kind of makes sense. It would be going out here. It would be attracted to both positives and want to go sort of down towards the left a little bit. Now, what if we built on this question a little bit? What if I also asked you, what is the electric field at the electron's location? Not the electric field from the electron, but what is the electron or electric field at the electron's location? Well, what you could do is kq over r squared for q1. You could do kq over r squared for q2, and then put the two electric fields together. But you've actually done that already. In this calculation right there, that is the electric field from Q1. There is the electric field for Q2. The easiest way to calculate an electric field is just force divided by Q. Well, you have the force already, and that force used the two electric field calculations to get them in the first place. The only thing that's different is that little Q in there. So if we introduce the Q back into the basic expression, if we take this force and divide it by the Q, the charge of the electron, we'll get the electric field. So if we take that 1.23 to the power of negative 12 and we divide it by the charge of an electron, we will get around 7.7 times 10 to the 6 newtons per coulomb, and that is the electric field at that location. So once you have the force on a charge, it's really easy to find the electric field. You just got to divide the Q out of the equation, and you've got it. Now, the direction for the electric field is also based on the exact same angle. Now, this one's a little bit different because here we have the electron. Of course, electrons go against the field. So if the electron wants to go down left, that means the electric field must be going upright. If it'd been a proton, they'd be going the exact same direction because positives go with the field. But in this case, it'd be going against the field. So the electron wants to go down left, which means the electric field is going upright, and it'd be going upright at 61 degrees. Okay, so again, once you have the electric field or the force, it's really easy to go back and forth. If you'd go back to the electric field questions you guys did, and you'd put a charge at that location, to find the force, all you have to do is F equals QE, and you've got the force on it. Okay, so let's try another question. Okay, so here we have 3-point charges all in a row. We got Q1, Q2, and we got the little Q, and we're going to find the force on a little tiny charge way over there. Okay, we make them yellow, that little guy right there. Okay, so we have two forces acting on it. There is force between Q1 and Q2, but we don't care about the force between those two. All we care about is the force on the little tiny charge over there. So same thing as before. I'm going to calculate my two forces. I'm going to calculate my force from number 1. So that's going to be KQ1Q over radius 1 squared. And the radius for number 1 would be the combination of those two distances together. And Q2 has nothing to do with it. So we've got the Q1, we've got the little q, and we've got the radius would be the 155 micrometers, and then we can calculate the force between number 1 and the little q. And then do the same type of thing. Force number 2 would be KQ2Q divided by radius 2 squared. And the radius for that one would just be the 80 micrometers. So we have all of our charges, we've got all our radii. Let's just find our forces, and then we can start piecing things together. Okay, so here are the two forces that I got. So let's look at the first one. I got 1.79 for the first one. Q1 is positive, and this little guy over here is also positive. So Q1 would push it away. So the force on that little guy would be towards the right for that one. Q2 is negative, so it would attract this one, so that force would be to the left. So that force would go this way. So now I can take those two forces and I can subtract them to get the total force. So the total force, or net force, would just be the difference between the two. So we got the 1.79, and we'll take away that 1.54 that's over there, and we've got 0.25 newtons, and this one's bigger, so it'd be going towards the right, and that would be the net force on Q, or the little tiny q that's on the right. Okay, so let's do the same type thing before. What is the electric field at Q's location? So what would the electric field be right here? So what's the electric field here? Well, you have the force. I mean, you could do the KQ over R squared, the KQ over squared, put them together if you want. But once you have the force, it's really, really easy to find the electric field. Just take the, if you want to find the electric field, this is going to be the force on it, and then just take the little q out of the situation. So if we take that 0.25 and we divide that by the 0.42 to the power of -9, because that was the little tiny q value, we've got an electric field of about 5.95 times 10 to the 8 newtons per coulomb. Now, this was a positive charge. The positive charge would go with the field. So if the force is towards the right, the electric field must be going towards the right, and this would be the net electric field or total electric field, however you want to look at it, but it'd be the combination of the two electric fields put together. So once again, once you have electric field, it's really easy to calculate force. If you've got the force, really easy to calculate electric field. It's just an application of the basic equation from grade 11. Once you have one of the two, the force or the electric field, either multiply by the q or divide by the q, and you can go back and forth between the other quantity really, really easily.